Hello, I am Ece Gürbüz. For this study, we work together with Özlem Turgut and Ibrahim Kök. I'm going to talk about our study titled Explainable AI-based malicious traffic detection and monitoring system in next-gen IoT healthcare. The Internet of Things is an innovative technology that enables physical devices connected to the Internet to communicate with each other and transfer data using standard communication protocols. IoT is prevalent in many fields, such as smart cities, smart homes, and smart buildings, and medical and health services. In this study, we focused on classifying attacks in network traffic data of IoT healthcare applications. The privacy and integrity of data in IoT-based healthcare systems are of utmost importance. Any data breach in healthcare systems can lead to serious health issues for patients. The importance of our study: machine learning and deep learning based intrusion detection systems are widely used to detect and prevent current risks. While ML and DL models have shown impressive success rates in detecting attacks, they are designed as black box models. These models don't provide information on how, why, and in what manner decisions are being made. There is a significant need for explainability, interpretability, and transparency in artificial intelligence models developed in the literature. Uh, Purpose of our study, we developed ML and DL models to classify attacks network traffic data in IoT health applications, and we employ explainable artificial intelligence methods to enhance the transparency and interpretability of the developed ML and DL model results. And we provide an explanation interface that makes all results understandable for healthcare professionals, experts, and patients. ML and DL models we used are k-nearest neighbors, random forest, decision tree, naive Bayes, support vector machine, multi-layer perceptron, and artificial neural network. XAI methods we used are Shapley additive explanations, local interpretable model agnostic explanations, explain like IM5, and integrated gradients. We worked with some tools such as Python, scikit-learn, XAI, Shapash, PyTorch, and Taptoon. What is explainable artificial intelligence? Traditional ML models don't provide explanations for why, how, and what decisions are made. Therefore, interpreting the results can be challenging. XAI refers to a set of processes and methods that enables users to understand and trust the results and decisions generated by ML algorithms. There are two types of explanations, global and local. Global explanations reveal the overall behavior of the model across the entire dataset, and local explanations are specific to each data point and provide insight into the reasoning behind the model's predictions. Our dataset. In this study, we used the intensive care unit dataset collected with open source data generation tool called IoT Flag in the study titled A Framework for Malicious Traffic Detection in IoT Healthcare Environment. Data traffic in the network was generated through the utilization of the IoT-based intensive care unit devices. In the dataset, there are 52 features. We worked with logistic regression to select the most important features. After feature selection, we worked with the 10 most important of 52. Algorithms classification results. ML and DL algorithms achieved classification accuracy ranging from approximately 95% to 99.5%. Among them, the random forest and decision tree algorithms demonstrated the highest success rates. LI5 global explanation. LI5 model identifies the levels of contribution for the 10 selected features across the entire dataset. The feature that contributes the most to the decisions is shown at the top and in a darker color, and the feature that contributes the least is shown at the bottom and a lighter color. Accordingly, the most contributing feature is TCP time delta for Li5 global explanation. Li5 local explanations. The local explainability results with the Li5 method are shown over the results of the most successful decision tree and random forest models. For local explanations with Li5, YAQ0 represents normal traffic and YAQ1 represents malicious traffic. Both models predicted that the selected data is normal traffic. And for random forest model, the most contributing feature is TCP time delta. However, for decision tree model, the most contributing feature is TCP flux push. Lime local explanations. In Lime, the charts in the top left display the prediction probabilities, which can be considered as a measure of confidence in the model's prediction. Decision tree model predicted with 92% probability, and random forest model predicted with 90% probability that the selected data is a malicious traffic. On the right side of the results, there are the contributions from the most to the least contributing features. In this graph, the features with blue color contribute that the selected data is normal traffic, and the other features with the orange color contribute that the selected data is malicious traffic. On the left side of these figures, there are the values of each feature for the selected data. SHAP global explanation. For SHAP global explanation, we use the summary plot. In this graph, the features are ranked according to their importance. For the SHAP method, the most important features contributing to the decisions are TCP time delta and frame time delta. For local explanations with SHAP, we used the first plot. For first plot, the feature which has the largest area is the most contributing to the decision, and the features with the blue color contribute to the normal traffic, and the red ones contribute to the malicious traffic. So according to the results, both models predicted that the selected data is a malicious traffic, and the most contributing feature is TCP time delta. Explainer interface. Shapash Monitor is an explanation interface that offers a user-friendly way to interpret and understand the results of ML models. In figure 10, the graph on the left side shows the importance of each feature as a global explainability. And on the right side, our dataset is shown. In this figure, graph on the left side shows contribution of the selected feature to the decisions. On the right side, there is a local explanation for the selected data from the dataset. So according to this result, TCP time delta is the feature that contributes most to the malicious traffic for the selected data. Explainability of DL models. Enhancing the explainability and interpretability of deep learning models is recognized as a crucial need in the literature. There is a trade-off between model accuracy and model explainability. So as model accuracy increases, model explainability becomes more difficult. Conversely, as model explainability increases, model accuracy decreases. While deep learning models generally have high accuracy results, their explainability are much more difficult than the other models. For the explainability of ANN, we use the integrated gradients. The integrated gradients method assigns an importance value to each feature, indicating how much each feature contributes to the prediction of the model. We selected the target value as 1, which means malicious. The values of the average feature importance were calculated according to the selected target value. So according to the result, TCP time delta and MQTT message type are the most contributing features to the decisions for the normal traffic. And TCP flux ACK and MQTT HDR flux are the most contributing features to the decisions for the malicious traffic. Finally, we presented an explainable malicious traffic detection and monitoring system based on ML and DL models to address the security and privacy concerns in IoT healthcare applications. The proposed system employs XAI methods to ensure the interpretability and explainability of the developed models. With XAI methods, global and local explanations of the model results are provided to make the results more understandable. Since there are a few studies in the literature focusing on DL explainability, DL explainability has been a problem addressed by this study. As a result, the study contributed to the transparency and of the developed ML and DL models and created a sense of trust in the decisions made by the models for the users. Thank you for listening.